Salut Cyril.
Right. So welcome everybody to the second edition of the GReTA-ExACT working group. It's a great pleasure to welcome today Cyril Cohen, who of course needs no introduction in the Cork community, but maybe for the non-experts in Cork here in the audience. So Cyril is an expert in the field, of course, and in particular, he has contributed also to this huge project, the mathematical components library and many other fields. And he will tell us today about hierarchy builder. And just before we start, a quick comment. If you wish to ask a question, maybe please put a quick note in the chat. We will also monitor the chat on YouTube, and you can always switch over from YouTube to the Zoom meeting if you wish. So this meeting will stay open and you can still register. And so another quick announcement, this year at the ICTT conference, we will have a special interest topic about all of this interaction between GReTA and Cork. So please have a look if you are interested at the Twitter account of GReTA, where we put the conference announcement. And so now, without further ado, many thanks, Cyril, for being here, and I hand over the word to you. Thank you.
Thank you for the introduction. Okay, so I will talk about a tool to make hierarchies of algebraic structures easy to write down in Cork. This is a collaborative work with Kazuhiko Sakaguchi and Enrico Tassi, and it's also it also benefited from the input of many people, especially during the port of the MathComp library to the tool, which occurred last April, if my memory is correct. Were not listed here, but they also deserve credit for all the bug reports and the experimentations with the tool. I'm going to start with very simple things, and as I go more into dependent type theory, I ask you to interrupt me if something is not clear at a very early stage, because then it will be only worse after that. So let's start with a very simple definition of what a structure is in mathematics, because we are going to build structures. So let's agree on what it is. If you disagree with this definition, raise your voice. Maybe your case will be encompassed anyway. So the definition for this talk will be a carrier, which can be a set in set theoretic foundations, or type in type theoretic foundations. Then there will be constants with values in this carrier and operations within this carrier, or maybe it can be predicates, which indicates whether some elements satisfy some property. And then a structure also needs a bunch of axioms to say which is the behavior of these constants. So, for example, I mean, one of the most simple example one could give, and I will do this talk with only simple examples, is the one of additive monoid. So I say additive because we need to name the operation, and we will call it add. So we need a type in type theory, T, a constant, which is the zero element, the neutral element for the operation, and a binary operation that we call add, which takes two elements of a type and gives back a type. So that's why it's T to T to T. So it takes one and two arguments and gives back an element in T. And then you need three axioms: the associativity for the addition, and then the left and right neutrality of the 0 with regard to the addition. Let's also set the context for this. I made a typo. Dependent type theory is the foundations we will use for this tool, because this tool was originally built for Coq, although it could be ported to other systems, I guess. And Coq is based on a flavor of dependent type theory called calculus of inductive constructions with lots of options, like cumulative universes that I will not talk about, but it's basically calculus of inductive constructions. There are other variants of this, but I will focus on the most generic aspects, which should be present in almost any dependent type theory as a foundation. So one thing you need to know about dependent type theory is that you can write terms that mix types and terms. So the types and terms live in the same world. So you can quantify on a natural number and then have a type that depends on this natural number. So it's going one step beyond polymorphism, since you can quantify on, for example, here a natural number. And then one important feature that we will use is that equality is a type. So you can define a type, constant EQ, which will give you a relation for any type, which will hold if two elements are equal, and which will not hold if two elements are not equal. I will not dive into all the subtleties, because depending on your type theory, you can even change the return type here, and you can interpret equality in another way. But here we'll stay with this basic definition of equality. And combined with dependent types, it allows you to express properties as type, as in for all n plus 0 equals n. Proof of this will be an inhabitant of this type. So this is the first things you need to know about dependent type theory with inequality. And then there are record types, which are types which hold a certain number of fields and may depend on a certain number of parameters. So this will become clearer with the examples. Next slide. But for now, know that in order to instantiate a record, the things you need to have are the parameters, and you need to also have some fields and apply the constructor of the record type to the fields to get an element of type RP1PN. In Coq, the keywords record and structures are synonyms, but we will be very specific about their use in order to inform the user about what we're talking about. A record will just be a set of fields like this, and a structure, we will reserve this keyword for mathematical structures from now on. That's why I'm using both keywords, even though they have absolutely no logical distinction in Coq. And there's a third keyword I will use, which is class, which is also logically a synonym of record and structure, except that Coq will attach some metadata to it. And for now, we will not care about this metadata, so you can also read this as a synonym. So let's go for our first record, which is one possible implementation of what a mathematical structure is in dependent type theory. And before coming to hierarchy builder as such, I will first go through all the possible encodings that people have tried in order to encode mathematical structures within dependent type theory. So this is one possible way, which was done in a paper from 2011. I think it's, I can't remember the name of the paper, but it's about the library known as math classes. And the strategy they use is to say that a structure is a record which they call class here, with as fields the axioms, and as parameters both the carrier and the constants, which means in order to quantify over a monoid, you need to quantify over t, 0, add, and a record of type ismonoid t0 add. So it means that you must first introduce a large context before you can even talk about what a monoid is. There is another approach, which is slightly lighter in terms of verbosity, which is the one used in Lean, but transposed to Coq, it gives the following. A monoid is a class that takes as a parameter only the carrier, and as fields, it will have the constants and the axioms. So I see there is a question. How does Coq know that 0 is 0 and add is plus there? Okay, I cheated in these slides because I didn't make the link. In order for Coq to know, you need to add a special directive after the record, which gives notations for inside the record. So I just omitted this, and but there is a way to tell Coq. Now, the whole problematic about algebraic structures is actually arranging them next to each other. So you need at least two to get interesting problems. So in this small example, the second structure I will give is a group. So how do you make a monoid from a group? Well, you say you need a monoid, and then you need an extra operation, which is the inverse for the addition, which we call up, like opposite, and two new axioms. This is only one of the two possible ways to extend the monoid into a group. The other way is to start from scratch and to say a type is a group and not monoid is a group, and list and repeat what was a monoid and add what it needs to be a group. So it's basically gluing those two together and saying now this is a group. So it's an additional representation. And once you do that, you realize that one of the axioms from before becomes irrelevant, because as soon as you have those two constellation properties here, you can deduce one of them. So in order to define a group from a monoid, you can indeed glue the two sets of operations and axioms, but you can also glue them and remove one line, and it will change nothing from a logic perspective. But from the perspective of the encoding, it changes everything. It means that there is one less argument to a record, which means that one constructor will have changed, and the code will be unstable if you just make that change without thinking twice about it. So this is only a very small example of things that happen in real life at a way larger scale. Because if this happens as soon as you talk about groups and monoid, imagine what happens when you talk about topological spaces, metric spaces, uniform spaces, complete spaces, fields, field extensions, so many things where there might be redundancy. So the meaning, so I have another question. The meaning of the monoid spec is to take a type T that is just a set and extend it to a monoid T. The meaning of the monoid spec is to take.
Sorry, maybe I can just explain what I wanted to understand
please.
here. So in algebraic specifications and in other areas, there are sort of parameterized specifications. That's what this reminded me of. So I've tried to understand whether whether you basically take a set T that represents the elements of the monoid, the elements from which you want to generate a monoid. Let's say if you're thinking about free monoids, let's say, and then you generate, then you add the monoid structure, and that generates your monoid. Or if so I'm trying to understand if there's a parametric element here in the specification, essentially, or whether or why do you give a type as an input to the monoid in the first place?
So this is because of this specific encoding. In this specific encoding, there is no type representing a monoid yet. It's going to appear in the next slide. For now, it's a characterization of which types can be seen as monoids. So in order to postulate a monoid, you need to postulate a type, which will be the type of the elements of the monoid. And then you need to postulate an element of type is monoid T, which will provide you with the rest of the of what you expect a monoid to be. So there is, I'm not sure I understood the part of your question about the free monoid, because there is no such thing as generating a monoid here. It's about specifying what a monoid is. Of course, if you build in a separate way, independently from this, the free monoid, you must be able to provide the zero, the add, and the laws that it satisfies, and proofs of the laws that are listed.
I think okay, so I think I get it. So what you're providing is essentially a predicate that you apply to an existing type, and that tells you whether that type is a monoid.
Yes.
Rather than something that you give a set to and that generates a monoid.
Exactly.
Which is the kind of free algebra kind of approach, but which is different because it's constructive, whereas yours is declarative. Okay, thanks.
Yes, that's it. That's the difference, indeed. So there is two other questions. How are sets and functions formalized? Does every type has an underlying set? So in type theory, there is no such thing as a primitive notion of set. A type is a collection of elements which belong only to this type and no other type. That's the major difference between set theory and type theory. In set, an element can belong to multiple different sets. In type theory, an element can only belong to one type. And you can define a notion of sets with this. I mean, you can name things that as sets in several different ways, but I don't want to talk about it. So let's not talk about sets at all for now. So let's say there are no sets in there, only types. And functions are a primitive notion in type theory as well, and correspond in constructive type theory to definable functions, actually computable functions. Does that answer the question of that left? Do I pronounce your name right? I'm sorry. Hello. Okay, let's come back to it later. Kind of, but graphs have sets as carriers. Yes, for example. I mean, it depends. I mean, in type theory, you could encode graphs in several ways, and one of the ways you can encode them is having vertices being a type. So the elements of this type will be the vertices. And you can either have a type for edges or make edges a subtype of the pairs of vertices. I mean, you have multiple choices, but none of them is canonical. Okay, let me answer the other question first. Are we free to use X multiple times in an equation defining the group structure? Yes, you can use, it's not, I mean, for example, here at 0R, you use X twice. So I'm not sure I understand the question. Is there an implicit coproduct that copies X? I'm not sure how to answer this question. I mean, it depends on your model, I guess. Okay, so I did answer your question, Konstantin.
Can I still, on the set issue, ask one more? So, can you hear me?
Yes, can we first close the
Sorry.
question of Konstantin just to be sure that this is okay?
Mm-hmm.
Okay. Yes, so you can go with that.
So yeah, I'm just asking this issue about sets because if you look at the standard definitions of graphs in these so-called algebraic approaches, single push-out rewriting, double push-out rewriting, you know, the view is graphs are algebras. So we have a set, which is the underlying carrier, and then there are two functions, at least, you know, source and target for the edges. So this is the standard definition there. So kind of my overall question is, if I have to do it in types now, has this any implications, or, you know, is it more complicated because I can't use standard operations on sets? So what is the relation here between sets and types?
I'm afraid the question is way beyond the scope.
Okay, you know, it's just, you know, if you look at the basic definition, you know, suppose I have almost no clue about COG, so now
Okay.
I'm going to read the handbook and want to formalize graphs, and I look at my well-known papers, you know, Hartmut Erich, graphs are algebras. Okay, so obviously this should be set. So now my problem is, okay, why do I have to do it a type? Or should I have it a type? Or do I convert sets into types or whatever?
Okay. So, I mean, this is a question of which foundations you're using. So inside type theory, the primitive object is type.
Yeah,
so
yeah.
As Hugo said, so Hugo says, as far as I understand, for the structure that I am defining and that Cyril are defining, with the standard mathematical one, only if you interpret type as set, which is indeed the assumption here, is that in type theory, wherever you can, you may replace usual uses of sets by type, knowing that it doesn't have exactly the same behavior. And then you can redo a lot of the literature with types instead of sets, and then you can sometimes work with subsets of a type, representing subsets as a predicate on the type. Mm. So in that way, you're using a type as a universe where all your elements will live, and within this universe, you can say there are subsets of this universe, and you can work within those sets. This is one way to define a set in type theory.
I mean, and just to say, I mean, it's possible to define a graph as a type of edges and two maps into a type of vertices, like you would do with sets. So, I mean, you should not be too.
Yeah, I'm sure you can do, but it's the question is about the relation to lots of existing literature. Okay, so I think that should be clarified.
Sure.
Yes.
Maybe just to give a very quick comment, we do plan to build up a set of examples. I mean, ultimately, we should exactly discuss these questions and have a little repository where we experiment with this.
Okay. Anyway, thanks.
Yeah, exactly.
That's some insight. Thank you.
Okay. So let me go on with this. Let's move on. Another way to encode mathematical structure is to go for a full bundling. So this time I write structure because it corresponds to a type that represents a mathematical structure. And the only thing I did is move the parameter from the is monoid before to a field. So when I do this, it's flat. Everything is inside a record, and in order to quantify on a monoid, I just need to quantify on one element of a monoid type, and I get everything I need to reason about a monoid. So this could be also seen as an object in the. I mean, elements of this could be seen as the object of the monoid category. It's one way to see it. Then there is a slight variation on this encoding that sort of reconciles the two approaches that I've mentioned earlier, which I will call, so this implementation I will call simplified packed classes. And it reintroduces the class from before, which left the type as a field, and reintroduces the structure as before, but instead of inlining the fields, it contains only two fields, one of them being the class, and the class contains the whole, the rest of the definition. This is particularly useful if you want to build hierarchies by successive extensions. When you move from this simplified packed class approach to a more complex packed class approach, which was described in a paper from 2009, which is the foundation of the mathematical algebraic hierarchy of MathComp. So the library for which this tool was mainly designed in the first place. This packed class approach, first, I mean, I abbreviated the contents of the field with this dot dot here. So if you say a monoid is first a class, I mean, I wrote record that it's a class here, and then you bundle the two together, then the only thing you need to define a group is to define what a group is from a monoid. Then to say a group is the packaging of the two previous records, one that states that it's a monoid and one that states that it's the monoid from the monoid of group, which was defined earlier. So this is group record packages both the is monoid and monoid is group records into a single one. And then we package everything again inside this structure, which is group type. So here, it's somehow the combination of the two words. So is there a question at this stage about this repackaging of everything? Okay, so we saw that there are many possibilities, and actually there are also many other possibilities that I didn't talk about, because the other possibilities that have been explored are actually did not scale in previous work. So in the other possibilities, you could encode mathematical structures as modules. You could also fully bundle a type classes, meaning putting everything inside and calling it a class, which is not a good idea, because it's not how type classes work. Then you can use telescope, meaning instead of packaging the classes, then repackaging the classes into records, you could include monoid inside, I mean the monoid type inside the group type directly, and say a group is a record that first contains a monoid and then the extra properties. So if I come back, it would amount to saying that instead of a group being a carrier and a class, which is the characterization for the carrier to be the group, you could imagine having here that a group type is a monoid and the extra properties you need for a monoid to be a group. But this doesn't scale either for complexity reasons. You could also use all the records that I mentioned before without any support from the assistant. And here I'm coming to the reasons why to do one representation compared to another. So what I said earlier, I mean, the approaches I fully presented are actually used For packed classes, they are used into the Coq MathComp library. The fully unbundled record are used in the Coq Math Classes library. The semi-bundled classes are used in Lean3 MathLib library, and AGDA uses a mixture of both. But actually, it's not. It would be, the story is not complete when I say that, because there is no way to use algebraic hierarchies without support, extra support from the proof assistant. So you need a bit more to work. So in Coq MathComp, we use canonical structures to help finding the structure associated to various types. In math classes in Coq, you need to use a mechanism called type classes, which is the analogous of Haskell type classes, and the same in MathLib. And without this help from the proof assistant, nothing would be comfortable to work with. And the choice of representation depends a lot on the tooling. You could not use packed classes with type classes, it wouldn't work. And you could not use canonical structures with fully unbundled or semi-bundled representation. I will not go into the details, but I would just want to point out that the technology of the proof assistant is instrumental in the choice of the representation, which is also a bit problematic because it means the choice you make are not tied to all are not only tied to the logical meaning of the structures. Do I consider that coercions are? Do I consider coercions as required tooling? Yes, I do consider coercions as required tooling, because otherwise it clutters the printing. I think they're instrumental as well. Okay. Additionally to that, in order to for all those libraries to work correctly, there are extra tools and extra boilerplate that is used in MathComp. Actually, in addition to the canonical, in addition to the records, there is a bunch of declaration to make to indicate to Coq how to infer that, for example, a field is also a ring, or to infer that the product of two fields is still a field, and so on. And it requires a lot of declaration that could be automated. And it even requires a validation tool to make sure that there was not a piece of code that is forgotten. In math classes, they also need a lot of boilerplate and hints in the inference. In MathLib, they also need some priority directive, like they need to add some annotation to say which rule is to be prioritized. And they also have a linting tool to check that people do not introduce looping instances and do not add instances of structures that would cause loops in the proof assistant, and so on. So none of these encoding are straightforward. You need tooling, you need expert knowledge. It needs more verbosity than actually just mentioning what should be the structure. And there are well-known design principles that might not be implemented correctly, especially by beginners or even forgetful experts. And there is a class of problems that one must pay attention and in order to work. So that's the problem that hierarchy builder addresses. Generating everything from the minimal amount of declaration, and providing replacing the expert support. So the purpose of hierarchies inside formalization is to factor theorems through those structures in order for theorems to be valid in the most general settings, and to automatically find which types hold which structure. So the requirement for a good hierarchy building tool would be to be able to declare easily new instances, to declare easily new structures, inserting them above, below, or in the middle of an existing hierarchy, handle diamonds, like if you have, I mean, there are so many variations that sometimes, for example, a commutative group can be seen both as a commutative monoid or a group, and both of them are semi-groups. You need to be able to handle this junction. And if you need to amend code, I mean, it must be easy to amend code. Then you need to provide several ways to instantiate a structure, because you don't. So for example, if you want to instantiate everything you need on rational numbers, you don't want to say, oh, okay, first rational numbers form a magma, then they form a monoid, then they form an additive group, and so on and so forth until you reach a field. And there are more complicated examples. So providing alternative ways is important. Predictability is also important. You might not be, you don't want to be able to infer two different incompatible structure on the same carrier. And also, when you add new declaration, it must not break user code. So this is a strong requirement in the tool. In the end, hierarchy builders provide two things: domain-specific language to generate and extend hierarchies from the minimal necessary input, and it lets you amend a hierarchy without breaking user code. So because of that, hierarchy builder needs to take care of a single design pattern used throughout a whole library. So once you use a hierarchy builder, you must not start defining things by hand. Okay, I have a question. So hierarchies are directed acyclic graphs, and we can instantiate a complicated structure in more than one way. Yes and yes. Well, you can see hierarchies as a directed acyclic graph of structures, indeed. And yes, you can. Yeah, I mean, do I have complicated examples? Well, I have a very simple example from the beginning of the talk, which is you can instantiate a group structure by first saying it's a monoid and then saying it's a group, but then you could have skipped one axiom. So instead, you should be able to directly say it's a group and skip the additional axiom. But there are also more complicated examples. For example, if you have something you know is a normed vector space, you should not need to say that it's a topological space and a metric space. You should be able to say it's a normed space, and because it's a normed space, it also it has the topology and the metric induced by the norm, and that's one way to instantiate structures that you could otherwise have instantiated by exhibiting the topology. And sometimes you can't skip it. For example, if you are constructing the product of two topological spaces, you don't have the norm space structure, so you must be able to say to define the topology directly. And when you know the two arguments you're making the product of normed vector spaces, then you could define the norm space on the product using the infinite norm, for example. So you need both. So in practice, hierarchy builder generates hierarchies using the packed class methodology, which was already used in mathematical components, slightly altering it to make it more systematic, since it used to be done entirely by hand before. Some shortcuts were sometimes used, or some packaging in some form was used to reduce the size of the code, but since it's generated now, we don't care about the size of the code as much. So we have in the DSL, we will distinguish two entities, mixins and factories. I will come back to it. And we can encode built-in sanity checks inside the tool so that we're aware of problems at an early stage and not at the point the user would use it. So I will now go into some examples. Like in those two, there are two different traditions depending on whether you're looking at things from algebra or calculus. So in algebra, it's customary to define things by extension of structures, like a group is a monoid extended with some stuff, a ring is a group extended with some stuff, and the field is a ring extended with some stuff. Whereas in calculus, in education at least, in my education at least, I was first acquainted with norm spaces, and one day told me, oh, but there is a generalization, which is the metric spaces. And then later in my curriculum, I learned that actually there was more general things such as topological spaces and so on. And that's why I wrote things in this way. It's the order that things are introduced for the students, but the arrows are reversed. From a group, you can deduce a monoid structure. From a ring, you can deduce a group, but it goes the other way compared to the education. A norm space, from a norm space, you can deduce a metric space and so on. So in these, and going through those arrows must be automated. If you know you have a norm space, you should be able to use the metric as if you had a metric space. And so these arrows represent both the notion of extension and the notion of an entailment. And it can be confusing. So actually, in our libraries, in MathComp and MathComp analysis, we have a range of algebraic and calculus structure, and we must organize the hierarchies as directed as secure graphs like this. And we notice that when we see things from the structure extension point of view, it's nice because we don't have to start from scratch every time. We can build objects incrementally, but it's also noisy because you don't have the internal definition. I mean, the internal definition of a structure is cluttered by the gluing of several things that come from several places. And it's also not robust because every time you want to cut a structure into bits, it means that it will change the internal representation. If you view things on the side of structural entailment, imagine that you reconstruct everything from scratch all the time, then it's more flexible because you don't need to cut things into small bits. You just say, this is a group. This is a ring, this is a norm vector space, independently of everything that was defined before, and you can link afterwards. It's robust because everything is fixed and set once and for all, but it's not suitable for inference because as soon as you deduce one structure from another one, it causes major problems in your type theory. I will not go into details, but this makes the view of let's define structures from scratch all the time and link them after the fact impossible to use in practice. So in order to reconcile those aspects, We use extension for the constructions that are used internally, and entailment for the user interface. In the end, the end user should see things as if they were all independent entities, but the way the tool will build the structure will always be by gluing entities called mixins together all the time. But we must, as a user, never know of which components every structure is made for real. So we must be abstract in the specific encoding of the structure. So we give 5 main primitives. The first one is how to declare a mixin. So a mixin is a record that might have dependencies and add some stuff to the dependencies. A factory looks like a mixin, except internally it will never be used directly. It will be compiled to mixins. And then factories must come with builders. A builder explains how to compile factories into mixins. And then we can glue factories, we can glue mixins into structures, but we don't need to be precise about which are the mixins that are used in practice. We must only tell roughly which components we use. And the 5th primitive is to instantiate a structure. Okay, I will give a demo right now, because this is, I'm afraid this could be obscure. Let's give a very concrete example about monoids. So I will switch to the demo right now. Oops. Stop the screen sharing. Stop the screen sharing. Okay, can you see? Can you see my screen? Okay, so here I'm going to define a mixin, which is a piece of structure that will be used internally, but only as a developer. I know it as a developer because I wrote mixin. That's the only indication. From the outside, when someone tries to use this mixin, they should not know whether it's a mixin or a factory. So in this mixin, I will say that there is a constant 0, an addition, and 3 axioms. So it corresponds to the class characterizing a monoid from before, except it has a special meaning for the proof assistant, because I said it's a mixin. And then I define a monoid as a structure which uses this mixin and this mixin only. And now, in order to define a monoid, I just need to provide an instance of this mixin, and it will build the monoid for me. If I look at so this expands to normal code. So for people who know how code looks like, here is the generated code. So it declares a module, it declares a set of it declares a record to hold the axioms. Then it declares several things, including the structure here, which would be the type of all monoids, and so on. So you can see here it's provided for us way more than just the few lines I wrote. So let's go to the next step of the example. So this was a single structure, so there is no problem as long as we have only one structure. So let's add a new one. Let's add a semi-group before the monoid. So now I can define first a semi-group, saying it's an addition, and an axiom. And from there, I can define what is a monoid from a semi-group by adding the 3 missing pieces from before. So this is all I need to say. And then a monoid is a semi-group and these extra components. And the problem here is that I broke the stability of the code because the is monoid record from before does not exist anymore. So here, there is no way I can reproduce the piece of code instantiating the monoid on the integers because there is no such thing as a way to build directly a monoid from integers. So what I will do in order to bridge the gap is add an extra piece of data, a factory, which is exactly the definition I had before for ismonoid. So this is compared to my first example, this mixin was converted to this factory by just changing this keyword, mixin to factory. And then I need to explain how to get back the pieces. So in order to get back the pieces, I need to explain how to get a semi-group back. So I just use this piece and this piece, and how to get the monoid, the is monoid from a semi-group back, which are the 2 other pieces. So these very simple declarations explain how to provide those 2 mixins here and there from this factory here, just by recombining the bits. And then I can define, hierarchy builder lets me define the monoid as before using this is monoid, and lets me define the monoid structure on Z as with exactly the same keywords as before, meaning that the user code didn't break. I will add an extra example, which is how to get to get a group from a monoid. So I will resume from where I was, meaning I had this monoid structure, and now I can define what is a group in 2 ways. As I said in the beginning, I can either say that a group is a monoid extended with those 3 pieces, or I can say that a group is definable from scratch by gluing inlining the 2 sets of operators and axiom and removing one which is not necessary. But then I need to explain how to get this one from this one. And in order to get the first one from the second one, I need to reconstruct the missing property here. And to reconstruct it, I can just prove it and then reconstruct it. So the proof is very simple. So it holds in a single line of code. And then I can reconstruct the whole structure. And then I can define the group structure on integers just by listing packaging all the properties together. And here you can see I can omit this right identity property. Okay, let me come back to the talk. Are there questions first, maybe on the demo?
Can I ask you one quickly? Sorry, I didn't write in the chat. So is that what you just demonstrated? Look like, I mean, you have a given code, and then you would have to start building this by hand. I mean, and the tool sort of allows you to repackage some pieces. Is that the correct way to look at it, or?
Yes.
Doesn't look very automatic, but I mean, maybe I missed something.
So the repackaging here is not the part that is handled by the tool. What the tool handles is the decision of how to build the record declarations and how to populate them from properties that you can give. Here, it could indeed be slightly more automated by saying, oh, you have almost all the pieces, let me just prove the one that's missing and do the rest. I mean, that would be a very simple optimization that I wish to do at some point. It could be, I mean, it would be minor compared to the rest of the automatic repackaging.
So your use case is more that somebody writes what could be a candidate, let's say for a library for something, and then you could look at it and optimize it by packaging some pieces like these direct definitions into factories, and then hopefully this will streamline a bit to a more, okay, I see. Okay, thank you.
Okay. Can Coq detect spurious axioms? No. I mean, as such, no. I guess you could try to implement a tool using SNTs or whatever that would try to deduce axioms from other axioms in order to check whether it was redundant. But this is not implemented to my knowledge, even less in hierarchy builder. Okay, other questions?
I don't know if it's only me or if it's of interest for others. Can you repeat the difference between factories and Mixin and the etymology of the name? So factory is the API somehow for the users, and Mixin is the implementation, internal implementation. Is that correct?
So, what?
Is that correct? View?
It's almost this. The difference, so every Mixin is a particular case of factory. And the factories are the API that is indeed presented to the user. So both Mixins and factories are usable for the end user in order to instantiate structure or to define new structures from existing ones. Internally, what changes is that only Mixins can be used as building pieces for structures.
So it's an effective implementation, the Mixin. Yeah.
So the Mixins are the basic blocks of the effective implementation that you never see. The Mixins are packed inside huge, big records that are called classes internally, and then they are included in structures. So the Mixins are used automatically by hierarchy builder as internal building blocks. And for the users, they are just factories like any other. And they must never know that some factories are compiled to Mixins and some Mixins are just used as such.
Okay, and there is a special etymology, or it's just ad hoc names like that?
So the etymology is partly inspired by the design pattern. Look, what's the name? And also, I mean, it's also the names that were used in informal conversations with Georges Gontier, although I'm not sure it's referred to exactly the same piece of code. So this vocabulary is inspired by some informal conversations and the design pattern book, which if someone has the name in mind, they can say it. And here it's, yes, in programming. And here the vocabulary is set in a very specific way. You have I mean, the builders are the things that build mixins from factories, for example. That's why we call them builders. But it's also a word in the design pattern book, which doesn't refer exactly to the same thing. So it was just convenient to see it as with these words.
Okay.
I will skip. I think we're near the end of the allocated time stop, so I will need to skip over the implementation. So I will just mention that the tool was implemented inside using a programming language called LP, which is a Prolog-like programming language, which is actually, so it's Prolog with extra stuff like binders and clauses that can be triggered. I mean, Enrico, if he's still here, can talk about it way better than I do, since he's one of the main developers. CockLP is a library in LP that allows to bind Coq API and use LP inside Coq to build whatever you like instead of typing it by hand. So it's a meta-programmation tool relying on the LP language. I will skip on what it does exactly. So it's a plugin that we use. It was nice to use. And so in the end, with the hierarchy builder, we have a high-level set of commands to declare structures and instances. We get the predictability of the inference because there are checks that are done at declaration time. We can take into account the evolution of knowledge, both of what is formalized and what the user has, because you can start with whatever knowledge you have and extend later. And if you started defining what a norm space was without having any notion of topological space, you can still come back and add what the definition of a topological space. And user code that didn't rely at all on topological spaces, and people who don't even need to know what a topological space is, can still use norm spaces as before. So this provides robustness regarding changes in the library and even in the internal implementation. It's nowadays it's approximately 3,500 lines of CockLP code. So it's and it takes into account structures with parameters and also morphisms. You can build hierarchies of morphisms. So we could, in principle, build. I mean, we have many ingredients to relate structures with each other. So right now we are still finishing porting the mathconf library to the tool. There are a few minor missing features that are work in progress, and it should be done in 2022, I hope. I shouldn't say such a thing, I'm sorry. I hope it will be done soon. There is still missing features to handle sub-objects like sub-rings, subgroups, and so on. And we also need some extensions to support multiple instances on the same carrier, but it should be non-invasive. I hope that we can achieve this by doing an extension of the tool, which will not affect the user code. And that's it. Thank you very much for listening. As of today, HB relies on canonical structures. What would happen if that was changed to rely on type classes? Could this be done without an impact on the user? Yes and no. The thing about type classes is that type classes are not, it's impossible to use a type class to represent a ring object. You can use a type class to characterize a type which would be a ring. I'm saying ring, for example. So hierarchy builder generates both classes without flagging them as type classes and structures. And the user code relies on the fact that hierarchy builder gives structures. So if you just remove canonical structures and keep type classes, you will not have the full part. I mean, this will impact the user code. But if you, let's say, remove canonical structures and make sure that all the features that were available on fully bundled structures are still available through type class resolution, then it should not impact user code. So it wouldn't require a substantial extension of unification in COC for a complete switch to type classes, not to impact user code. Do you see what I mean, Theo? What is a realistic roadmap? Exactly. Can you, are you able to speak? I think it would be easier for me to.
Actually, just quickly, I think I will stop the YouTube live stream so we can all go more into gallery mode and open discussion. So if anybody is still on YouTube, please join us on the Zoom meeting, and I'll just quickly stop because this might be easier to just have simply the microphone open. Yes. So I'm just